Okay. Hello, everyone. So we start our series of 4 lectures dedicated to chain complexes and codes. And so first, I will start from classical LDPC codes, which in the language of chain complexes can be considered as like one-dimensional chain complexes. Okay. Let me first remind you some standard definitions that I'm pretty sure you very well know, just to fix the notation. So we will use this symbol for our ground, for our main field, which almost in all cases will be just field of 2 elements. And so we consider linear codes. And as you know, any linear code can be represented by its parity check matrix as a kernel of this matrix. And another way to represent a linear code is by using so-called Tanner graph. So it's bipartite graph. So here we have checks. Here we have our bits. So we have n bits. We have m checks. So our matrix is m by n matrix. So let me also draw the matrix. Okay. N and bits and m checks. Okay, and so what we call an NKD code, also called a linear code. So it's a code defined by, for example, some parity check matrix that has the following parameters. So we have the dimension, just the dimension of the space. We have minimum distance, which you also know that for linear codes, so you can define it just like as weight, as a minimum weight of non-zero code word. So and n is the number of bits. Okay, and what you already saw in the previous lectures on coding theory is that there are good codes, and there's also a bound that shows that sufficiently good codes exist. Okay, and it is usually called Gilbert-Varshamov bound, and in asymptotic regime it looks like this. Okay, and so what it says that for sufficiently, so as n tends to infinity, yes, so we have codes which have rates at least some constant, some non-zero constant. And you saw there was a proof that use some greedy-like algorithm, but in fact, you can also prove it in a different and also very interesting method. So let me briefly remind you what is this method. So first of all, let us just for fun calculate. So first of all, we are interested in the number of non-zero code words of weight less than d. Yes, and so let us just calculate their number. So yeah, we substitute the parity check matrix. So here I use the standard notation, which equals to 1. So this thing is equal to 1 if this is satisfied, and it is equal to 0 it's like an indicator function, yes? And it is equal to 0 if it is not satisfied. So this is just the number of code words of a given code, yes, given by the parity check matrix H that has weight less than D. And now the magic trick is just to take the expectation. And so we just take a random matrix, uniformly random matrix, and you just calculate the same quality. And what we get, so since expectation is linear, yes, we also can rewrite it in a different form. Okay, and so what is this guy? So this is expectation of this function that just returns either 1 or 0, yes? And this expectation is just exactly the probability, yes, the probability of this event for a random parity check matrix. But let us just estimate this probability. So what we have here? So what is H multiplied by C? So we just take, so we have C, we have ones in the C, and we just add some columns of this matrix, yes? But since this matrix is completely random, uniformly random, so when we add all these random columns, we have a completely uniformly random vector. And of course, this probability is equal to what? Okay, so it's, so we can estimate this as 1 to the n minus k, where n minus k, this is our n minus k, yes? And here is the size of the ball, of the Hamming ball, size d minus 1. And the magic trick is that if this value is no more than 1, then this value is strictly less than 1, yes? And here I should also say that here we exclude all 0 code words. So this here we have a strict less sign, yes? And so what we have that if we if we calculate this expectation value, then then we have that this value is smaller than 1, which means then there exists such a matrix, yes, for which this quantity is equal to 0, because this quantity is integer, yes? And so it means that we have this code, and we prove it by a completely different technique, as you see. But the bound is the same, if you remember from the first lecture. Okay, and so just some small exercise. You can try to prove yourself. So prove that a random matrix random H has full rank, is full rank. And by the way, I forgot to say that, of course, all this idea, it also says much more. It not only say that it not only say that we have a matrix, but it also says that we have a lot of matrices. In fact, almost any binary matrix give you a very good code. So if we choose at random, because this quantity can be very small, yes, if we increase this one. And so, this is an exercise that shows that random matrix is also a full rank. Okay, so so the main reason why I reminded you this very useful technique, because this is one of the main methods that is used to prove, so originally was used to prove that classical LDPC codes exist. And so let me first tell what is LDPC code. So what I mean by LDPC code. So by LDPC code, I mean that the matrix H is sparse. So by sparse, I usually mean that, so we have an infinite collection of codes, and each row and each column just bounded by some constant. Okay, so for example, so typical maybe example, so just consider the code where every column has 3 non-zero elements and every row has 4 non-zero elements. Okay, and so LDPC codes were introduced by Gallagher in '60s in his PhD thesis. And what he showed in his thesis, maybe it's the most influential PhD thesis in information theory, I would say. And what he showed was really amazing. So he showed that random LDPC codes are good. And by good, here I mean that these parameters, K and D, yes, grows linearly. This is a common definition of a good code. And he also, he showed it using some similar arguments. This is exactly why I showed you. He just used some more sophisticated ideas, because here you have sparse matrix, so you have some little bit more difficult distribution. So but you can work on it and you get very similar results. And what he also showed that you can, why we need sparse? You can ask why we need sparse matrices. Well, first of all, it is very convenient to represent a sparse matrix in practice. And Gallagher wanted to construct some practical codes. And another reason, also very, very important, that you need also to decode this code. And he introduced two decoding algorithms that are in our modern terms are usually referred as belief propagation. And another one is bit flipping. So he didn't use exactly bit flipping, but he used a very similar method. And this is the last one is exactly the one that you saw in the previous lectures in the Sipser-Spielman construction. Yes, so bit flipping is just we look at the bit, yes, just look at the number of unsatisfied checks, and if it is too large, yes, so you flip this bit, and you do it iteratively, and this algorithm was already in the Gallagher thesis. And another one is the belief propagation, so it's much more complicated algorithm that it involves some probability. So usually for practical codes, you also have some estimates of the bits. You don't know just whether they 0 or 1, but you also have some probabilities, and you can utilize these probabilities. And there's also very interesting decoder called belief propagation. Okay, and let me show, so I said that random LDPC codes are good, but let me show maybe some example. What do I mean by random LDPC code? Because different people mean different things when talk about random LDPC code. So by random, completely random, I mean the code constructed in the following way. So first, we start with a set of checks and set of bits. Then we fix some degrees. Yes, we have bits x1, xn. We have checks z1, zm. And we have check some degrees, and we okay. And we check the degrees such that the total degree for all these ones is exactly matches the total degrees, sum of the degrees of the in this part. And then, so we just choose some random permutation. So here we have the same number of half edges, and here we also have something like half edges, but here we have some random permutation. And this permutation says how we connect all this. And this is one of the standard models for random LDPC codes. And for, so you can see that there could be some problems, technical problems. For example, this bit can be connected to this check, and then it can be connected to this check again. But on average, for random graphs, so you have this with very, very small probability, this vanishing probability. And for typical LDPC codes, so you do not have this problem. Okay, but what I described to you right now is something that's really good. So you can prove theorems about it, yes. But for practice, we need more structure. And for practical applications, what we usually use, we use a much more refined approach where, let me call it LDPC. Sorry?
The model you're given, the degree sequences for the checksum and the bits, and then you pick the random.
Yeah.
That's part of the input.
Yeah. And this is completely random, so uniformly random permutation. Yeah. And so for practical applications, so we need some combination of structure and randomness. Yes? So here we have a completely random LDPC code, but if you want to use these codes in practice, for example, in 5G, in Wi-Fi, and etc., you need more structure. And because there are many reasons why you need this, because in hardware it is really hard to implement arbitrary permutation. So there are a lot of technical problems. And also these codes with some structure are easier to analyze and represent. And so here the main idea is the notion of the lift of the, or if you algebraic topologists, you maybe know, if you're topologist, you know the notion of L-fold covering. And so let me briefly remind you what it is. So we start with a small graph, which is called the base graph. And what we do, we pick some orientation. So just let us assume that all edges are oriented. And we also fix some set that we call fiber. And we assign to each edge, to each oriented edge. So let me put it like this. We assign a permutation of the element of the all permutation on the set F. So sim F is a set of all bijections on the set F. Yeah? Fiber is just a set. Fiber is a set. Just arbitrary set. Arbitrary set, yes. Finite set. And how we get this lift. This is called L lift. So we replace each vertex with L corpus, and fiber is a set of size L. Okay, let us fix the size of the fiber. So we have L corpus, so it means that V of G alpha is equal to V of G multiplied by fiber. And we also do the same with edges. But the most interesting part is how we connect, yes, how we connect edges with vertices. And this is exactly where we use these functions. Sometimes it is called labeling, sometimes it's called lifting map, and so different people call it differently. So here we use this permutation. So here, so we assume that this set is indexed by the elements of F, and we connect X with the element alpha E X. So in fact, so we have some matching, some perfect matching here between these two parts, which is given by this permutation. Very simple. And so we have L times larger graph, and it is called L lift. And let me switch to codes because I'm supposed to talk about codes. So for codes, we have the same idea. Since every LDPC code can be described by a graph, by a Tanner graph, so we can apply this idea to codes as well. So we start with a small LDPC code. Maybe it's not LDPC, just code. Yes, and we apply this idea. So we lift it. So we assign permutation. So here I use some particular example. So here I use what is called group lift. So we have a group, and we have this permutation, which is given by X plus S modulo 3 here, yes? So this is our fiber. This is our fiber. Yes? And here are our assignments. So we assign shifts. Yes, so here in this case, we just assign some shifts. And in this part, you can see what you get. Yes, so this guy is just converted to 3 parallel lines. Yes, because it's a 0 shift. But this guy is converted to shift by 2 elements. And here, so in fiber, as I said, yes, we have some. Of course, in each fiber, we enumerate our elements by the elements of the fiber. So this is a key idea. And why it is very interesting, because you can also describe, and this type of lifts, these are not the most general ones, yes, but here we use, as you see, some group, yes, and multiplication in the group or addition in the group. And why this is interesting, because you can also describe in a very nice way, algebraically, the code that you obtain. And here, so we, in this specific case, so we can describe this code as a code over a ring, not over a field, which is very interesting. So instead of F, we go up to the ring, and this ring is what is usually called a group algebra. So what is a group algebra? I'm not sure whether everyone is familiar with this concept or not. So, okay, let me just very briefly remind. So group algebra is just elements of the group algebra, just formal linear combinations of the group elements, and so we can, so of course we can add them in a very natural way, but we can also multiply them in a very natural way. Yes, because so we just multiply elements of the group, yes, and okay. I think that it should be clear. And in our specific case, so we can say even more. So when we have this particular group, yes, cyclic group, so this ring is the same as the ring of polynomials. Yeah, in this specific case. And this works, so you can easily, yes, see that we have polynomials, yes, so typical element would be and x cube is equal to 1 again, yes? So very, very easy. And this allows us to describe the code words, yes? This code as a subset of the ring, of the, so we can consider it like a non-binary code. Yes, our alphabet would be not field elements, but our alphabet would be the elements of the ring. And everything works exactly like in standard coding theory. Yes, the only difference is we change field to the ring. Okay. And here you can see the parity check matrix, which is, of course, is obtained from these shifts. And here's a natural question, whether we can get good codes using this idea. And the answer is yes, at least if we start from complete graphs, then, so every such complete graph, of course, has rate at least 1 is m to the n. And there's a quite old result by Sridharan and co-authors that shows that this idea, in fact, so let us consider just, for example, this example. Yes, here we get an infinite family of codes. And what they show that if you choose randomly these permutations, then with high probability, you get good code. And here and so here it's, so I should emphasize that this is for SL, yes? This is quite important. And here is my question to you. So what do you think happens if we change this SL to, for example, cyclic group of size L? What is your best guess? What will happen? What's the distance we would have? So here, yes, the distance grows like at least like the size of the lift, the distance of the code. And what happens if we just replace by cyclic group? Anyone wants to guess? And so quite surprisingly, so the distance that we get here is just constant. And in fact, if you replace this as L by any abelian group, you still get constant. So it doesn't grow. So we have very sharp transition when we go from abelian group to this non-abelian group. And let me let me briefly yes.
Is there any reasoning why abelian group is more?
No. For non-abelian, we get linear distance. Yes. So as L, the lift size. So here, it's since we start from the constant size object, yes, we get linear distance. But if we change this set of all possible permutations only to permutations like shifts, yes, or any other abelian group, then we do not have this good property. And what is interesting that all codes that are used like in 5G, in Wi-Fi, yes, they all are based on cyclic group, which means that, yes, we as theoretical people, we of course are very interested in proving theorem, yes, but people who work in practice, they just need to construct some code that works. And it doesn't stop them that from theoretical perspective, this is an awful code. And in fact, they work very well in practice. Though their distance is bounded by a constant, because this constant is quite large. And for this reason, we do not have any problems with this. Okay? Okay, that's a good question. So that is what I'm going to explain right now. So, yeah? So here I should give a comment. So when I mean abelian, so I mean that this permutation is given like a group multiplication. Yes, so it's not just a abelian subgroup. So it's very important that it's like a regular action of a group. Yeah, for any abelian group, yes. That not only for cyclic groups. And in fact, let me just show the magic trick that shows that this is in fact true. Yeah. 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 Yeah, they compute, and you are exactly right. This is when we consider this as a block matrix, yes, each of these elements is replaced. So if you want the binary representation of this large code, then each this element is replaced by L block, and all these blocks, as you said, yes, they commute with each other, and this is exactly the reason of this problem. But the problem is that, so you would expect that maybe this distance would be linear, but maybe it's still be quite large. But in fact, it is just bounded by a constant, which is really fascinating, I would say. And so the trick here is the following. So let me just explain it on this example, and you will see. So we need just to give an example of a code word of a small weight. And let us try to do it for this particular matrix. So we need to provide a code words. A code word, as I said, so it's a vector with elements from R. And so we have 2 by 3 matrix. Is there any method that allows you to give a non-zero code word from the matrix? Any analytical method? Do you know of any? Okay, let me show you one. So it's very simple. So we just use this matrix. And we just add, for example, the first So we need somehow find the dependencies in the columns. Yes, find some coefficients such that if we add these columns with these coefficients from the ring, then we should have a zero. And so, and the idea is just to consider a square matrix where we duplicate, for example, let us duplicate the first row. And what we have right now, now we have a square matrix. And for square matrices, we can calculate determinant. And this determinant is, it is of course, it should have determinant equal to what? To zero, of course, yes? Because we have two identical rows here. But we can also calculate this determinant using the standard formula. Let us use this row. So we have x0 plus determinant for matrix, for this matrix. Okay, then we have x2 multiplied by determinant of this matrix. And we have 0 multiplied by the determinant of this matrix. Okay, let us call this A1, A2, and A3. So these determinants. And these determinants are polynomials, yes? And so we can calculate them, yes? So this vector so here it's x3 is equal to 1, and here x0, so it's 0, and here it is x1, and here it is x0 plus x. Am I right? Yes? Okay. And now we can also do this trick with the second row. Sorry. A1 is. Oh, okay. Sorry. Yes, it's 1. Yes, thank you. So now we can do this with the second row. And we will have some similar calculations that will show that x0 multiplied by A1 plus x0 multiplied by A2 and x1 multiplied by A3, yes, is equal to 0. So we have two equations. Yes, we have two equations. So the first equation is this one, and the second one is this one. So what we see that this vector is a code word of this matrix, for this matrix, because it satisfies this parity check in polynomials and this parity check. So the first one, this parity check in polynomials, and the second one is the second parity check in polynomials. So we see that this is a code word. So this is a code word. Kernel of this matrix. Okay, and now we see that if we increase the leaf size, yes, if we increase the leaf size, then we do not have increase the weight of this example. Yes, the weight will still be constant. And this trick, of course, yeah, so I do not give you the full proof, but here just the main idea, yes? So the main idea is that when you grow this size of the lift, so you have, every time you have some example of a small weight code word. Of course, I omitted some important details. For example, sometimes all these three may be equal to 0, but you can work on this, and so there's no problem for this. So the actual proof is a little bit harder. Okay. Is it clear? Any questions on this? Okay. Let us move to the next part. Okay. What next? So next we want, as a theoretical computer scientist, as a scientist, we want something that we can prove some properties of it. Yes, so for what I described to you, this is what, yes. It's not abelian, so why this argument doesn't work? Because, so you do not have determinant. Determinant is only defined for matrices or abelian rings. So it's not even defined for non-abelian. So you cannot even define it. So this is the main problem. This is exactly when it fails. Okay. So let us, so we have some structure, which is given by the lift, but we still want, now we want some explicit construction. So we can further ask whether we can maintain the same structure, which is very useful, yes, because you can represent code words as non-binary, some non-binary vectors, and you can see, so it's quite handful. And the answer is yes, you can even give the explicit construction that has good distance. And here, so let me remind main ideas that are used to construct good codes using expanders. So here where we need to use expanders. So as you know from the previous lectures, random graphs, regular graphs are good lossless vertex expanders, which means that the number of vertices, so it was denoted like this. It's almost as large as possible. And you already saw that using this idea, so we can use this idea if we take a random bipartite graph. Yes, you have a lossless expander on the random, yes, and it has these properties. And this graph has a lot of unique neighbors, and this means that it was already also mentioned and proved before, maybe in the second or the third day, that this gives you what I usually call alpha beta expansion. Expansion, which I define in the following way. So this is alpha beta expansion of the parity check matrix. What do I mean by this? I mean that if we have a sufficiently small vector, then it violates a sufficiently large number of checks. And alpha beta are some fixed constants. And in fact, since you have unique neighbor expansion, yes, you have a lot of unique neighbors. And these unique neighbors, the number of these unique neighbors grows at least linearly with the code size, if you remember this from the previous lectures. And in fact, you, you can also show that this happens with the Sipser-Spielman codes also. So it grows at least, so for some, of course, this x is non-zero, of course, yes?
Beta times the weight of
sorry? Oh, yeah. Sorry. Yeah, yes, of course. Yes, exactly. Okay. But if you remember from the previous lectures, our Sipser-Spielman construction works. So what they use spectral expanders, not random expanders, like calligraphs, yes? And here we have what is sometimes called lossless edge expansion, which means that we have the number of edges that is almost as large as possible. And let me briefly, how many? Okay, 8 minutes. I think that's enough. Let me briefly remind what was the construction. So it's just a Tanner code obtained from graph and from small code defined by small parity check matrix H. And it is just as, so you put your bits on the edges, yes, and when you restrict your for each vertex, when you restrict this string to the neighborhood of the vertex, yes, we have element of this local code. So if we just can draw it in the picture like that, yes, we have graph, and in each vertex we have a parity check matrix that checks these bits, yes, that whether they satisfy it or not. And if everything is satisfied, then we have a valid code word. This is the idea of the Tanner, and so Sipser-Spielman showed that with like Ramanujan calligraphs that are very good spectral expanders. So we have this property, and in particular, so we can also show that you also have this property. Yes, not only good linear distance, but also linear growth of unsatisfied checks. But it takes a little bit more time, so let me just briefly remind you how it is done. So we have a graph, so we have some graph, like spectral expander that let's, for simplicity, assume that it is it has good two-sided spectral expansion. And from mixing lemma, so we can prove that yes. So this quantity, yes. What
do you mean by?
Oh, okay. EFS is the number of edges that goes outside of S. Okay, let me, yes.
The size of S is still bounded by epsilon times.
Yes. This is all for sufficiently small sets. So lossless expanders are also always defined for small. This is small. Small, yes. Yeah, thank you. So, and ES is the number of edges that goes outside. And so for mixing lemma, you know that this thing is quite small. Yes, it's like, if I remember correctly, so it's no more than, if we, let us assume that S is, the size of S is alpha n, alpha is the number of vertices, yes, then okay, so it's, I wrote it correctly, so it is at least, so we have this kind of estimate from mixing lemma. So it says, so here alpha is a parameter that controls how small this set S, yes, and we can make it arbitrarily small. So this part is, so this is just exercise. You can derive this bound using mixing lemma. And here, lambda is our spectral gap, and here the delta is a degree of the graph. So we have degree denoted by delta. Delta is the degree of the graph, the large delta. Okay. This is the standard d divided by the length of the code. Or let me maybe n, because we use n for the number of vertices. And so here, what you can see that this thing is small. So because so if your yeah.
Should be alpha times delta and the little delta, and the little delta should be capital delta divided by degree divided by
it's alpha divided by no, it's not degree. It's like
you want it to be uniform.
okay. So sorry. Let me just maybe. Okay. let me just I need to double check this. So let me just describe it because I don't have just enough time. So the main point here is that the number of edges, so the size, so what we need to show that if we have some sufficiently small code words, that it involves small number of edges. Since it involves small number of edges, this edge is connected to small number of vertices. And we need to estimate the size of the set that is connected, that has zero syndromes. Yes, that has all vertices where all the checks are satisfied. And here, what you can show using this mixing lemma, that the size of this set is also very small. So this is the main idea. And why I mentioned this is because you can also show some similar result, but not for H, but also for transposed code, what is called a transposed code. And in fact, for transposed code, it is even much simpler. It is even much simpler. So so typically when we consider Tanner codes, we do not consider, so we consider just standard code defined by, yes, so this is code defined by kernel, where H is the parity check matrix of the Tanner code. But we can also consider the code that is defined by transposed code. And it turns out that this code is also very interesting, yes, and it has the following interpretation. So we still have the same graph, yes. Now we choose some, so since it's transposed code, yes, so this is a metric parity check matrix of the tenor graph. So we need to show, so we consider linear combination of the rows, not of the columns of the matrix. And here, when we work in the reverse direction, so my main point is that, so in the original Sipser-Spielmann construction, yes, you need to control the minimum distance of the local code, which should be at least square root of degree of the graph, plus maybe some epsilon. But if you also want the same properties from this transpose code, yes, but by the same properties, I mean these properties, alpha beta expansion. So you also need to have that the dual code of this local code has large minimum distance. Okay, and why the dual code? Because here we work in the different direction. And here H, in this direction, when we consider transpose code, work as a generator matrix. Yes, because we generate the linear combination of the rows. Yes, and here we have these elements of H. And it works as a generator matrix since it is, and it means that this is a dual code. And we need to control the dual code. Okay, I think I'm done for today. So let us, okay, maybe after. So after that, I will show you that you can also construct these codes with some additional structure. Okay? Any questions? Sorry? Yeah? Yeah? Yeah. So here I just suggest use the parity check matrix of the Sipser-Spielmann code and consider transpose. It also can define some. But this, in fact, this depends on the local and the dimension of the local code. If you choose the dimension in the correct way, so you can have even dimension for the transpose code. But here my point is this, that even without dimension, so you can have this property, because this property doesn't depend on dimension. It doesn't require, it's just a property if you multiply by the matrix. Yes, so the property of the matrix. It doesn't depend. This one doesn't depend on dimension. It works even for codes with dimension 0. So what we're trying to prove? We're trying to prove that the parity check matrix has this expansion. So we're not talking about the codes here. We are talking about parity check matrices, that they have this small set expansion property. This is the main point. Okay. Yeah, that's exactly. And as I said, so we do not, so maybe it's the correct way is not to consider as a code, yes? So, but of course, we can also define a code, and sometimes it will have non-zero dimension. But it is very non-standard code. But if you're interested in the interpretation of this code, it has also very interesting interpretation, because this code can be interpreted in the following way. So we just put code words here from the dual code, and each edge, from each vertex, in each vertex, we put some code word. Yes, and this code word gives you what you should put on these edges. And you do it for all vertices. And then you see whether these bits agree with each other. If we have these vertices and these vertices, if they agree, then it's okay. is good. And if edges agrees, then we have a code word. So the code word has also a very interesting interpretation. Yes, we put small code words to each vertex. Then after that, we have also bits on each edge. And for each edge, each vertex provides two different estimates what it should be. And if they all agree, then we have a valid code word. And it is also, as you see, related with agreement testing. So we have some local codes that have some intersections, and if they all agree, yes, then this is a code word. So I think this is the code word also interesting in its own right. So you can also study it, and it's not very well studied, I would say. There are very, very small number of papers that consider such a code. Yeah. Okay.
The second X has a label of 2, which means we should have a shift of
Here.
What's that?
on the diagram of.
Okay.
So this X has a label of 2. But we see that happening for this vertex, or for the vertex on the right.
This vertex. Maybe you can show.
So this means that there should be a shift of
Shift
2
equal to
edge
2.
in the lift.
Yeah, 0 goes to 2. We just add to 0, 2, and we connect 0 to 2. We connect 1, 1 plus 2, modulo 3.
It happens
Yes.
from this side to this side,
Yes,
and not from
yes.
this side
For
to this side.
each edge is replaced with perfect matching that corresponds to this permutation. And as I said, so we have some fixed orientation. Yes, this is also important because otherwise you would have problem. Okay?
Now.
Fine? Okay? Yeah? Sorry, what transposed? Okay, that's a good question. So my interest in this transpose code, yes, it comes from the application to quantum LDPC codes. And this is what I'm going to describe in the next lectures, because right now it's just an interesting object, yes, to study, but the motivation, so we do not have motivation. And the main motivation are quantum LDPC codes, because for quantum LDPC codes, you're always interested in codes in both directions, I would say. And this is exactly when it is required. Okay. Any other questions? Comments? Okay, let us take a break.